lesson in geometry for the 2020 spring trimester. Two congruent chord theorems. Mainly we're working on chords in this next to last unit. And there's basically a theorem and a converse. So I'm going to go through that, an example, and then finally do a short proof. Beginning with two congruent chord theorem. So this is kind of like a definition, except we could prove this, so it's not a definition. But if two chords are equidistant, what does it mean to be equidistant? Well, equidistance is measured from the center, yes, of the circle. So here is the distance in blue. And again, that distance would have to be perpendicular. So if those two distances are the same, then the chords are congruent. All right? And then we have the converse of that. Say you have two chords, right? A, B, C, D. Say those two chords are congruent. So if AB is congruent to CD, then the distances, so in this case, not very straight, but you get the idea. We'll put a little perpendicular sign there to show that those distances are straight. And again, we should probably mark this ORP, or whatever three letters you choose. Then, guess we already have then the distance is OR is congruent to OP. All right, here we are using that particular definition, the theorem. In this case, we have two congruent chords, and then we know the two distances from the chord to the center. So, algebra problem, simple, 4x plus 19 equals 12x minus 5. Here we go. Look at us solve, so smart. X equals 3. Careful, don't get excited, they wanted OP, so make sure you go back and plug 3 in. I think we get 31. All right. And finally, a little proof. ABC, isosceles. We have two segments that are perpendicular, and so we've kind of marked those in the diagram. I marked the base angles for the isosceles triangle. We certainly probably should be marking the sides as being congruent, but it makes it kind of messy, so we'll leave that off. One of the important things that you need to do as you do proofs is ask yourself, what do I need to show to prove that that's isosceles? Well, you could approach this from two ways. You could say, I'm going to go for those two sides. Or you could say, I'm going to go for that angle and that angle. Either one would prove to you that that triangle is isosceles. I think in this problem here, the sides are better to go for, a little bit shorter. Main reason is the theorem that we dealt with is, well, look at that. If you have those showing up in your proof, let's use them. Okay. So here we go. I think a 3-letter proof, or a 4-step proof. 3-letter. All right. If the triangle is isosceles, then we know that AB is congruent to BC. And that's by definition of isosceles triangle. Line 3. If those segments are congruent, they're actually chords, then we can say, oh, guess what? The distances PQ and PR have to be the same. And those are marked as perpendicular, so they have to be distances. Line 4. If those two segments are congruent, then triangle PQR is isosceles. The key step here is step 3. Right? This would be the converse of the congruent chords theorem.